All right. So welcome everyone for today's coaching seminar in differential algebra. It's my pleasure to introduce Rémi Jaoui from CNRS Lyon, and he will speak about on the density of strongly minimal algebraic vector fields.
So thank you for the introduction and for the invitation. I hope you can hear me well. So I will talk about the notion of strong minimality in differential algebra. So this is about the interaction between two areas of mathematics, one in model theory, a branch of mathematical logic, and the other one is differential algebra of characteristic zero. And I will talk about a specific notion about this interaction, which is the notion of strongly minimal systems of algebraic differential equation. And before starting to explain some concrete mathematics, let me give you a bit of history. So this interaction started in 1968 with the notion of a differentially closed field, which was studied by Leonard Bloom. And it took a couple of years to understand what was the important part of this interaction. And in the article of Scheller about differentially closed field, this is where it was identified that this notion I'm going to talk about, the notion of strong minimality, was lied at the center of this interaction. But these strongly minimal systems of algebraic differential equation were mysterious for quite some time, and a breakthrough happened in the 90s with the work of Richovsky, where he gives essentially a full description of the transcendence properties of the solutions of such equation or such systems of equations. And he gives a striking application with the proof of the Mordell conjecture for function fields of characteristic zero from this description. And so last date that I want to give is 2011 and the work of Ronnie and Anand Pillay on the model theoretic study of Painlevé equation. And as a byproduct of their analysis, they realized that actually a parallel treatment of this idea can be traced back to the work of Painlevé and its collaborators. And so I have two objectives of my talks. I will first give a fairly long introduction about this notion for people that are not familiar with model theory. And my main goal will be to explain you how it can be useful to prove transcendent statements. And the second part will be on my title, to explain how to construct many examples of strongly minimal systems of ordinary differential equation. So if you have questions, please do not hesitate to ask them in the chat or on Zoom, and I will try to answer them. Okay, so what is the typical problem of transcendence that I want to talk about? It's the following. You're given two kinds of data. The first data you're given is a family of order 2 linear differential equations. So the second derivative of a function y, which is the unknown, is a linear combination of the function y and the derivative of y. And this linear combination depends on two rational functions. And these two rational functions depend on themselves on some complex parameter. And you're given a second kind of data, a family this time of nonlinear differential equation. So the second derivative of y also depends on y prime, and the time variable, but this time the dependence is as a rational function and not necessarily as a linear function. And the kind of problem you want to answer is that you give me a bunch of parameters for the linear equation. You give me a bunch of parameters for the algebraic equation. So everything referring to the linear part will always be in green, and everything referring to something which is algebraic and nonlinear will always be in blue. And so you ask me, okay, I give you these parameters for the linear equation, this parameter for the algebraic equation. Does there exist some solutions of your linear equation relatively to these parameters, and some solutions of your algebraic equation relatively to these parameters? So this solution should be non-algebraic, such that all these solutions together satisfy a non-trivial algebraic relation. They vanish on a polynomial which involves a time variable t. And when no such relation exists, I will say that the functions are algebraically independent. So to explain this principle, I will give you an example. As the linear equation, I will take the family of Bessel differential equation, which is this particular family of linear equation, which has a singularity at t is equal to 0 and a singularity at infinity. And for the family of algebraic equation, I will take a specific family, a subfamily of linear equation that we have studied with Vonnie Naglu, James Freitag, and Dave Marker, of the following form. The second derivative of y is equal to the first derivative of y times the rational function of y, which has, as you see, a pole in minus beta. And so in this case, and that's why I chose this example, we can completely answer the previous question, is that if you give me parameters, if they don't satisfy some very particular configuration, then the solutions of this equation, so you have to assume that you take a non-zero solution of the linear equation and a non-constant solution of the algebraic equation. For any choice that you make of solutions, they will automatically be algebraically independent over C of t. And so what is this configuration? The alpha I, the coefficient for the Bessel equation, have not to be 1/2 plus integers, and the beta I has not to be square root of -1. So these are conditions about the parameters, and you have conditions about pairs of parameters. The sum and the difference of the alpha i's are not integers, and this polynomial x times x squared plus 1 cannot take the same value for all the beta I and the beta j. And the theorem is sharp in the sense that if these conditions are violated, then you can pick actual solutions of the equation such that they are algebraically dependent. And so this corollary is proved using strong minimality, and I'd like to explain you how strong minimality shows up in the proof. And so the first part I will discuss is the linear part, the green part of the statement. And so many of you must be familiar with this statement, which is a theorem of Colchin from 68, which actually goes back to Siegel, but I haven't actually looked at the paper of Siegel. And it says that under the green condition, the alpha i's are not 1/2 plus integers, and the sum and the difference of the alpha i's are never integers, then the solutions of the linear equations are algebraically independent. And so I want to give you some ideas about the proof of this theorem, because we will try to mimic the same idea for the algebraic part. And so the first thing I will do is to transform this second order linear equation into a system of order 1 linear equations, but with 2 variables. So you take the solution, the Bessel function and its derivative. They satisfy together a system of 2 variables, which is given by the matrix that I wrote below, which, as you see, the coefficients are exactly the coefficient of the linear function. And so so in that case, because we have a linear equation, we will use a differential Galois theory. Is that a question? Yeah. Okay, and so to this system, differential Galois theory associates an algebraic group, which is called the Galois group of the system, which is equipped with a faithful representation. That is, you have an embedding of an algebraic embedding of this algebraic group inside the group of 2x2 matrices, and this is a very powerful device to transform transcendent statements, such as the one I wrote before, into problems about algebraic groups. And so what are the interpretation of the 2 conditions that were written? So the first thing is that in the case of this equation, it's not hard to see that this representations always take value in the special linear group. Yes. The group of a matrix of determinant 1. And the first condition tells you that the Galois group is as big as possible. This is the special linear group. The interpretation of the second condition, or more precisely, the negation of the second condition, that the sum and the difference of the alpha I and alpha j's are not integer, tells you that the systems are, so if they are a sum and the difference are in integers, it tells you that the systems are gauge equivalent, What does that mean? That the systems are gauge equivalent. If you're given two linear systems, they are gauge equivalent. If you can find a linear change of coordinates, such that this linear change of coordinates sends the solution of the first system to the solution of the second system. And so there's a very nice way, a compact way to write that down using linear algebra is that you can find a matrix, an invertible matrix with coefficient in phi of t alg, which are actually, so you allow your change of coordinate to depend on the time variable, and we change the matrix A of t to the matrix B of t. But you see that since we are doing differential algebra, this is not the PA P minus 1 that appears in linear algebra, but you have a second term where the derivative of the matrix P is involved, and by the derivative of the matrix P, I mean the matrix where you differentiate all the coefficients. And so when you have understood the right interpretation for the two conditions, the key lemma in the proof of this independence is that if you're given R systems of dimension 2, and that their Galois group is SL2 of C, so which was ensured by the first condition, and that 2 by 2, the systems are not gauge equivalent, then actually, if you pick non-zero solution of these systems, they will be algebraically independent over the field of function of one variable. And the proof is to use some algebraic group theory about the group SL2 of C and the Galois correspondence. And so we want for the blue part of the statement, the algebraic part of the statement, we want to use the similar strategy, but we don't have a Galois group. We don't have the Galois group to use this lemma, and we need to find an analog. And the analog will be given by the notion of strong minimality. So let me do the setup for the blue part. So you start with the family of equation, the same family of equation as before. And you consider a solution of this equation. And then if you take it with its derivative, then it satisfies a system of order 2 equation, of equation with two variables, but the system, each equation has order 1. So the system I wrote here is the first derivative of y1 is y2, and y2 prime is y2 times f beta of y1. But you see that you have to make sure that everything is well defined. The function f beta of y has a pole in minus beta, so we will assume that y1 plus beta is not equal to 0. And to move from the equation E beta to the system S beta, I have to multiply by y prime. And so I will assume in the system S beta that y2 is not equal to 0. And so this is the main object I will be studying in this talk. So I will give the general definition. A system of autonomous algebraic differential equation with n variable is similar. This is a system given as previously. You have n variable. The derivative of each variable is given by a rational function of the previous variable, and you have an inequality which ensures that all the rational functions that you pick are well defined everywhere. And so the way to write that is that you're given the inequality is given by a non-zero polynomial, and all your rational function, their poles should lie on this curve. And so what that means is that this rational function, they are not polynomials, but they are in the localization of the polynomial rings along the inequality G not equal to 0.
Question.
Question. Yes.
So this differential equation E of beta, is it just an example to illustrate the definition, or it's a main example you're going to follow for some other reasons?
So this is the example that I will use to illustrate the definition, because we can compute explicitly on this family. This family, this example, I will explain why I chose this example, but this is for illustrating the general definition. Okay, I will move in the second part of my talk to other kind of equation. Okay. And
Excuse me. I have also a question, because this equation you choose it's in fact it's a Riccati equation. So in fact you can associate some kind of Galois group for this, because the solutions are quotients. Sorry?
This is not a Riccati equation.
if you integrate in time, both ways, the f yes, because there is a log. Okay.
Yes. This is
But
not a
this
rickety
transformation
equation.
to S beta, you managed to transform it to a linear system, or?
So I will explain that the solutions of E beta are algebraically independent of the solutions of all linear differential equations.
Okay,
So this
but
is
you
not
don't use the specific form of this equation where you can go back to linear
No.
system. No. Okay.
No,
Sorry.
this is an example to illustrate. I will show you a bit more. So you can replace f beta by any rational function of y.
Okay.
I just pick a specific one parameter family to have only one parameter.
Okay. Sorry.
Okay. But so the important assumption that I will make in all this talk is that I will only consider systems of ordinary differential equation that do not depend explicitly on the time variable. And this will lead to various simplification. It's not that what I'm saying is not possible to carry out if you assume that you have your rational function have a coefficient dependent on the time variable, but during all my talk, all the systems I will consider will not depend explicitly on the time variable. Okay. And so what does that mean that such a system is strongly minimal? So this is, I want to give two definitions, which will be the two definitions of my talk. So if you consider a system as previously, to say that this is strongly minimal, it means that for every differential field that you can pick, which extend, so the base differential field, which here is a field of complex number endowed with the zero derivation, and for every solution of your system S that you pick, so where do you pick it? In some differential field extension of L, then you have only two possibilities for the transcendence degree of the field generated by L and Y bar over L. This is either equal to 0 or equal to n. And so you see in the definition there are two quantifications, one over all differential field and one over all solutions. And the one which make this definition powerful, but also hard to check in practice, is the quantification over every differential field. And so let me first explain what happens if you don't do this quantification. So what gives you this condition for when you take the field L to be equal to C? And so to this system of equation, you can associate a differential ring, which is the localization of the polynomial ring along the inequality G equal to 0 that I explained before. And on this ring, you have the partial derivative along the xi, which are derivation on this ring, and you just take the weighted sum weighted by the function which appear in your system. And so differential algebra tells you that every time you pick a differential prime ideal in your differential ring, you are going to be able to find a solution of S such that the field it generates over C is exactly the fraction field of your differential ring mod out where you mod out this idea. And so what strong minimality implies that this can have transcendence degree, has to have transcendence degree 0 or n. And so this means that every non-trivial prime differential ideal of your differential ring is a maximal ideal of your ring. Okay. Because if it has a transcendence degree 0, then it is a maximal ideal. And if it has a transcendence degree n, then this is a 0 ideal. And so what are the consequences?
Question. Yeah, maybe we're going to talk about anyway. So these are sort of algebra ways of giving the definition. Are there any kind of analytic ODE applied math versions of this definition?
So I'll give here what is the consequence of what I've said, okay? But just in the case where L is equal to C, okay? Here I'm giving the consequence just for L is equal to C. Okay, if you want this definition for the quantification over all differential field is the one that is hard to write in an analytic perspective. But if you fix L is equal to C, this definition in particular means the following thing, that so you have your equation, you have the set where, so inequality defines the forbidden set in red, where you cannot go. And so this property that you have that every non-trivial differential ideal is maximal, it tells you that your system has finitely many. The first thing it tells you, equilibrium points or singular points. So what are the equilibrium points? They are, or the singular points, they are the points where all the Fi's vanishes. Okay, so there are finitely many points where all the Fi vanishes. And if you take a solution which is not one of these singular points, so a solution which is non-constant, then it has to be Zariski dense in your space. Okay? Because if you take the Zariski closure of this solution, the Zariski closure will be defined by an ideal, which is the differential ideal. So all strongly minimal systems look like that, but as we will see, it's not enough for a system to look like that to be strongly minimal. So
and there are systems that don't look like this, right?
There are systems that don't look like this. Yes. Okay. If you don't assume strongly minimal, you have systems with first of all with some solutions that are algebraic. You have systems that have infinitely many singular points. So this is one consequence of strong minimality, which I will call weak minimality in the second part of my talk. But this is not all systems look like that. This is a non-trivial consequence, the first non-trivial consequence of strong minimality. And so the second definition I want to give is the notion which will play the role of gauge equivalence in that I described for linear equations. So if you give yourself two strongly minimal systems of autonomous ordinary differential equation, what is an algebraic correspondence between these two systems? An algebraic correspondence, this is a change of coordinates. So you're going to write the coordinate of the second system in terms as function of the coordinate of the first system. And the functions that will appear, they are not rational functions, but they are not far, they are algebraic functions. So they are algebraic over the field of rational functions of n variables. And you assume two things about your change of variables. First of all, it has to be locally invertible at the generic point. So the Jacobian of this change of coordinate has to be not zero everywhere. So not zero everywhere, so that it's not zero at the generic point. And the second thing that you ask is that your change of variables sends the solution of your first system to the solutions of your second system. And so algebraically, so it's a bit harder than in the linear case. You have this very easy way to write that using linear algebra. Here, it's a bit harder to write what you mean by send solutions of S to send solutions of T. So you can write it algebraically. The graph of your change of coordinates can be identified with a closed subvariety of the product spaces. And the fact that it sends solutions of S to solutions of T means that the ideal defining this subvariety is the differential ideal in the tensor product of the differential rings associated to these two systems. Okay? So if you want to think about it analytically, you have the two systems that I explained. We assume that they are strongly minimal, so they have the description I wrote before. And your change of variables have a ramification locus. The ramification locus is the place where the Jacobian of the change of variable vanishes. And everywhere outside of this ramification locus, you can find locally analytic branches of this algebraic change of variables. And because I told you that all solutions are Zariski dense in the space, all solutions will go out of the ramification locus. And so when they go out of the ramification locus, you can compose them with these local analytic branches. And the property that it sends solutions of S to solutions of T means that when you do that, and you take a solutions of S, you will get solutions of T. So these are the...
yeah, Rémi, so you're using here that we are in the autonomous setting, right? So that non-orthogonality is like witnessed without parameters, essentially, right?
Here I'm defining weak orthogonality.
And for autonomous, that's enough, right?
Yes. Yeah. So if you assume that things depend on the time variable, that's why I'm saying I'm making this assumption from the beginning everywhere to simplify all the argument. Things have are more complicated when you allow a time variable, but you can still carry out many things in the time variable things, if you assume things depend on the time variable. And so so now that I've given the two main definitions, let me explain how we are going to do the proof for the blue part. So let me consider a bit more general setting, because this f beta of y was very puzzling. So we are going to take any equation of the form y double prime divided by y prime is equal to a rational function of y, any function of y, and you consider the associated system with two variables. And so the good point about this family is that the two notions that I've defined previously, we can exactly compute when they happen. The system is strongly minimal if and only if your function has a non-zero residue around some complex point. And if you take two strongly minimal systems, so two systems satisfying one, then they are in algebraic correspondence if and only if you can find an element of the affine group such that F and G differ by precomposition by an element on the affine group. Okay, this is a theorem we proved with James Freytag, Dave Marker, and Ronnie Naglu. And so in particular, you can apply it for this particular family that I picked. And you see that it gives you the interpretation of the blue condition, the fact that beta I square is not, the beta is not a square root of -1. It exactly means that you see that beta square plus 1 is exactly the residue at minus beta. So it exactly tells you that S of beta I is strongly minimal because it has a non-zero residue. And the condition not B tells you that the systems are, so if these two polynomials are equal, this happens if and only if the two systems are in algebraic correspondence. And so now that we have the interpretation for the two conditions, we need the analog of what I described previously as a Colchin-Key lemma. And what is given by Colchin-Key lemma is this description of transcendence property of strongly minimal set of Reshevsky that I mentioned in my introduction. And so here I'm using again in a very strong form that the equation do not depend on the time variable. And so if you consider for I is equal to 1 to R, an integer, which will be the number of variables of your system, and you assume that all the systems have more than two variables. Otherwise, you have to do things a bit differently. I don't want to talk about the case of one variable. And you consider for each I a strongly minimal system of autonomous ordinary differential equation with ni variable. So the assumption that the system is strongly minimal. And you consider for each of these systems a non-constant solution of this system. And so if you have an algebraic relation between all these functions all together, so if the transcendence degree of all these functions all together is smaller than what you expect, the maximal transcendence degree, then it means that you can find two of these systems such that, okay, the first thing is that they have the same number of variables. I only define algebraic correspondences for systems with the same number of variables. And you can find an algebraic correspondence between these two systems. And so you see in the blue part of the statement, the first assumption, they all have the same number of variables, but the condition B ensures that they never an algebraic correspondence between them. Okay, so I've explained the green part, I've explained the blue part. I'd like to explain how to glue them together. And there's a very easy way to glue these statements together. If you have a very general way, if you have R system of strongly minimal autonomous differential equation with more than two variables, and S systems of linear differential equation, if you take solutions of the strongly minimal systems and solution of the linear systems, then they are actually always independent, in the sense that if you compute the transcendence degree of all these functions taken together, it always decomposes in the most simple way as a blue part, a system that only involves the strongly minimal part, and a system that only involves the linear part. And so you see, by doing differential Galois theory to prove the green part, and by doing strong minimality to prove the blue part, you get the transcendence statement that I've written here. So this is what.
Excuse me. Are you assuming
Yes.
R not equal to S here?
No, R can be equal to S. It's any R and S.
Then why doesn't the previous result say that they should be they would be strictly less than? the sum?
I didn't understand the question.
Well, in the previous slide, you have a
Yes.
result, right? Yeah,
Yes.
which says that if they are strictly less, then two of them would be equal in number, right?
Yes.
I see. The converse doesn't work. Is
So-
that correct? You're saying?
No, so here I'm talking, so what I'm saying here is that if the blue part here is strictly less than N1 plus NR, but here I'm talking just about what happens when you put together the two statements. Okay, but I don't talk, so they can have, if this is not maximal, if this is not the sum of the Ni, then actually two are equal of the Ni, but you can pick as many systems as you want. Okay, it doesn't matter how many algebraic system and how many linear systems.
Charlotte,
So
What are the numbers? What are the number variables in these Z bars? Are they the same Ni, or do they use different
they can
MIs?
they can
MJs?
have Mi variable. It doesn't matter the number of variable of the Li. The only important thing about the number of variable is that all the strongly minimal systems have more than two variables.
Okay.
If they had one variable, the only thing where this lemma is not true is if you take systems of one variable and your linear equation are actually exponentials. But I mean, the Galois group is a GN to the power n. But the important thing is that you take more than two variables. There's no assumption on the number of variables of the SI, except that they have more than two.
No, I'm asking the relation between the number of variables in the L's.
In the else, there's no assumption on the number of variables. It can be any number of variables.
Any number. Okay.
Okay, but I haven't said anything about what this transcendence degree is. This green part of the transcendence degree has to be computed.
But what if you take L to be S?
If you take R to be S, then you just have the same number of systems. But I mean, it means that the system cannot be strongly minimal and linear at the same time. And this is a very strong form of that.
What? Why?
The system cannot be because of this.
What? You're saying that the system L cannot be strongly minimal in this result?
The system S are strongly minimal,
Yeah,
but the system L, they are systems of linear equation.
And linear equations are not strongly minimal?
Exactly. This is implied by this statement. This is a strong form of saying that you cannot be both strongly minimal and linear, except if you have only one variable. Does that answer? So I should have said it explicitly, but strong minimality, it doesn't replace what you need to know how to do doing differential Galois theory for linear equation. Is something that you do when you have equations that are really nonlinear and that you cannot linearize, that are not Riccati equations, that you cannot associate a Galois group. I mean, at least you cannot in the classical sense. So, okay, so the summary
Charlotte has a question, sorry.
Yes.
Are you again? Just to have could we have a hint on how you prove that the system SI are strongly minimal?
Charlotte, it's hard to hear you.
Okay. Is it better?
Yes.
No. Yeah.
Yes, much
So
better.
I would like to know if there is a way to explain shortly on how you are proving that the system SI are strongly minimal. It seems like it's very close to a proof on differential forms. Are you using this kind of argument?
So here we are using a concrete argument computing with Puiseux series for this particular system. But I will explain in the second part of my talk how to construct strongly minimal system. Okay, so another kind of argument that allows you to construct strongly minimal system. But in this equation, the specific shape of the equation is such that we can make concrete computation using Puiseux series, and we don't need a lot of a formal approach using the differential forms to do this part. What we use differential form for is for the second part, for computing the algebraic correspondences between these systems. But the proof of strong minimality is a computation in Puiseux series. And so the things that I want you to remember for the second part of my talk is that, okay, if you take a strongly minimal system, then the system is weakly minimal in the sense that the singular set of the system is finite and every non-constant analytic solution of your system is Zariski dense in the space. The second thing that we see that is important is that if you have strongly minimal systems of autonomous ordinary equation, then computing the algebraic relation between the solution of this system amounts to computing the pairwise algebraic correspondences between the systems. And the third thing is that you can take everything you know how to do using differential Galois theory and glue it with everything you can do using strong minimal systems. And so one of the hard questions of the topic is how do you show that a system is strongly minimal? And another hard question is how do you show that two strongly minimal systems are or are not in algebraic correspondence? So to explain this, so an example is that until the work of Casal, Freytag, and Naglu on Schwarzian equation, actually, till 2020, if you restrict to the autonomous case, we knew some non-autonomous example, but in the autonomous setting, there was very few examples of such systems. We knew essentially one example, which is called the Poisson equation, and this is the case beta is equal to 0 of the family I've described you before. And the question that goes back to the article of Sheila, who was mentioning its introduction, is that true that for any n greater equal to 2, does there exist a strongly minimal system of autonomous differential equation with n variable and integer coefficient? Okay, so very early on, the question came up as, do this system exist? And actually, to study Sheila's question, Poisson conjecture something which is neither stronger nor weaker. It's that actually a sufficiently general system of ordinary differential equation or of autonomous ordinary differential equation with n variables is always strongly minimal. And so I'm going to explain this an answer to this conjecture in the autonomous setting. So when you assume that your systems are systems of autonomous ordinary differential equation. And so if your systems, I just want to say that there are 3 different settings when you can ask these questions and where what you mean by a sufficiently general system change a lot. You can ask for autonomous ordinary differential equations, so the thing that I've been explaining so far, and this is what I'm going to do. But you can also assume that for ordinary differential equation, that is when the functions fi depend on the time t, the coefficients of the polynomial of your function depends on the time t. And you can also ask for highly non-autonomous systems of ordinary differential equation when the coefficient of your polynomials are meromorphic function, arbitrary holomorphic function on a complex disk. And the first thing I want to explain is that the answer to the third case is known, and it's a recent theorem from Matthew David-Biss and James Freytag, which says that if you take the complex disk of radius 1 and you consider a highly non-autonomous differential equation, so differential equation where which is given by a polynomial such that the coefficient of this polynomial are holomorphic function. If you assume that your polynomial f has degree greater or equal to 6, and that the coefficient of that appears in your polynomial are differentially independent and differentially transcendental function over Q1, then the systems that you get is strongly minimal. And the only comment I want to make is that this system tells you actually that most highly non-autonomous differential equations are strongly minimal. Why? Because in a complete metric space, what do you call a typical property? A typical property is a property that holds for every point outside of a countable union of closed subset with empty interior. And if you look at the holomorphic function on the unit disk, this is a complete metric space. And if you look at the tuples of functions that satisfy this property of being differentially independent and differentially transcendental functions, actually this set is contained in the complement of a countable union of closed subset with empty interior. So in this sense, most highly non-autonomous differential equation are strongly minimal. So the theorem that I want to present is the autonomous version of this theorem, and something that is a bit nicer is that we can work with finite dimensional vector space instead of these parameter space here, which are very big parameter spaces. And so if you take the finite dimensional complex vector space of systems, so you denote by K and D, the finite dimensional complex vector space of systems of the following form. So you have two variables, n and d. N is the number of variables of your systems. And now I'm looking at the systems are not rational functions, but polynomial functions. And you assume that this polynomial have total degree less or equal to d. And so if you assume the simplest thing that you can assume, that n and d are greater or equal to 2, if d is equal to 1, actually the system is linear. So you know that this is not strongly minimal. If you assume that d is greater or equal to 2 and the number of variables is greater or equal to 2, and you consider the set that I call the exceptional set of ND, the set of systems in this class which are not strongly minimal, then this exceptional set is small in the sense that it is contained in a countable union of proper Zariski closed subset of K and D. Okay, so the set of systems that are not strongly minimal is small. Okay. So what does that mean? It means that from a complex analytic perspective, it gives you all the information that you want, because it tells you that every time you pick a system from your family and you pick an epsilon, you look at the ball around your system of radius epsilon, and you look at the number of systems that are strongly minimal in that ball, and actually it always has full Lebesgue measure in this ball. Okay, so most systems are strongly minimal in this sense, and in contrast to the previous case I presented, you don't have to care about the norm or anything because you have finite dimensional vector space. And so before this result, no systems of autonomous ordinary differential equation with 4 variables or more was known. So this is an improvement on this direction, because it shows that there are many in all number of variables. But on the other hand, if you think more from an arithmetic perspective, it doesn't give you all the information that you would like. For example, if you think about Shellard's question, it doesn't produce any strongly minimal system defined over the algebraic closure of Q. Okay, it doesn't even show that there is a finite transcendence degree extension of Q, such that for every n, this finite transcendence degree extension of Q admits a strongly minimal systems with parameter from this finite transcendence degree extension. And so more generally, something that I'd like to understand better is the fine structure of this exponential set. There are some very easy questions that I'm not able to answer. For example, I'm telling you that it's contained in a countable union of proper Zariski closed subset. Is it itself a countable union of proper Zariski closed subset? And the second, the interesting question is how this set intersects the rational or integer points. And so there's various questions about this, what the set of not strongly minimal systems look like in this family that I'd like to study. So, okay, so I will finish soon, but I just want to present a more abstract version of this result, which is where you replace the affine space by an arbitrary, the complement of a hypersurface in an arbitrary smooth projective variety. So you pick your favorite smooth projective algebraic variety of dimension n greater or equal to 2, and you do the following thing. You start by embedding your subvariety inside the projective space. And then you pick an hyperplane in your projective space, and you intersect it with your variety in such a way so you can always find hyperplanes that intersect your variety in a smooth way. And so you put this hyperplane at infinity. The complement of this hyperplane is an affine space of a large dimension, and you embed the complement of your projective variety of this smooth hyperplane inside the affine space of big dimension. And so what you consider instead of this vector fields of degree less or equal to d, you consider the space of regular vector fields on your variety which have a pole of order less or equal to d at infinity. And so in that setting, you get the same theorem, but asymptotically, there exists a constant D0, which actually depends on the choice of X and your hyperplane HX. And that can be arbitrarily large, such that every time you take a D greater or equal to D0, the set of elements or the set of vectors that define non-strongly minimal system is small. That is, it is contained in a countable union of proper directly closed subsets. Okay, and so I had a couple of slides about the proof, but my time is done. So I will stop here. And if you have questions about the proof, I can give you some information after. Oh, thank you for your attention.
Thank you. Let us thank Rémi. So do we have any questions for him?
I have a question, if I could ask. Hi, Rémi.
Hello.
So do any of the examples of, I can't remember, are any of the examples of Brestovsky over the constants and order 2?
I guess so, yeah. I think so.
Rémi, or Jim, can you translate your question into an
Oh, yeah, sure. Sure. Is it true that, in this paper of Brestovsky, there are some autonomous order 2 nonlinear equations given that are strongly minimal? I just couldn't remember.
I do think so. You mean about my comment that we didn't know any before 2020?
Yeah.
Yes.
But I think none of his are.
It was not well known.
Yeah. Oh, I see. None of his are over Q. Maybe none of his have rational coefficients or even algebraic. I think.
Yes. Yeah. I don't remember the paper enough, but this example, in order to this is some. I mean, okay. So they are never given by polynomials. They are always given by rational functions. So it's a bit like our example here is that you have to allow rational function with poles. Right?
Yeah.
It's a bit like this theorem. Up here, this kind of equation that we studied, the condition to be strongly minimal is that f of y has a non-zero residue around some complex point, and so f of y cannot be a polynomial. And I think that in Brestovsky example, it's the same. They can never be polynomial, but I think some of them are autonomous equations, but they are not given by polynomial.
Right.
Of course, you can always multiply, but then if you multiply, you can add some curve. So I mean, it's true that somehow there were many things, and also there's many examples which were not autonomous that were known, but not that many families.
Right. Yeah. In fact, I think you can find a comprehensive list in the paper of Matthew and I.
Okay.
Yeah. So that's a remark. And one other remark. There is one more, but only a single equation of order 3 that was known before. I entered it in the chat, and it was never in a published paper, but it is in my thesis.
Yes, I remember Dave mentioning it in one of his talks.
Yeah. It's not a very good proof, though. So, okay.
Any other questions?
So so you mentioned a lot equations for order 2, right? But do you have a lot of results for high order equations? Like you seem to focus on order 2.
So there are examples of order 2 that I gave here, which is a family that we know how to compute. So this theorem gives an abstract existence statement in all orders, but where actually equations are known, there are this equation in the autonomous case, right? There are this equation of order 2 as the families of equations that are known, and they are Schwarzian equations in order 3, right, which were studied by Guy Casal, Voninaglu, and James Freytag. So we know large families where we can compute actually these notions in order 2 and in order 3. Starting at order 4, there's really no known example. Somehow we don't have good enough methods so that the computation can be carried out for order 4.
Thank you. And is this property that's rarely occurs or almost always occurs?
I didn't hear
Strong
the question.
minimality. Is this a rare property, or it's something that's generically true?
So the theorem the theorem tells you that this is generically true. Right? It tells you that the set of elements that are not strongly minimal has Lebesgue measure 0. So if you take any system, right, you can if you fix an epsilon positive, almost all systems around this system will be strongly minimal, in the sense that the set of strongly minimal systems around your system will have full Lebesgue measure in the ball. So if you pick a system at random, it will be strongly minimal. It's a bit like picking real numbers at random.
Very nice, thank you.
Charlotte, you have a question?
So the first one, so
Could you move your microphone, please?
Sorry, is it better? So you
Yeah.
gave us a genericity result on strongly minimal property. Okay, my first question was about how you prove for a specific system that it is strongly minimal. Does your strategy for genericity proof and the strategy for a specific system have something in common, or could you explain briefly how we can prove that something is strongly minimal?
So so here the proof that I'm using here, and this is a common thing that happen in other examples, is that you associate to your algebraic system a linear system, and there's various ways in the example. The way you associate the linear systems is very different. But in the generic case, I take the simplest equation you can write, and which is just you take the partial derivatives of your function along the yj's, and you get a linear system. And actually, you will compare the Galois group. You take conditions on the Galois group on this linear system that will give you when this system is strongly minimal or not, plus a bit of information. So often, what happens is that you have your parameter depends on a variable. Your system it's rare that you have a unique system. Usually your systems comes depending in a family, depending on some parameters. And what you try to do is to associate for each parameter a linear equation depending on the parameter, such that actually the set where it's not strongly minimal correspond to the set of points where the Galois group is smaller than the generic Galois group. And so this kind of exceptional set that I wrote here, if I want to understand its better structure, I think that you have to try to write it down as, I mean, it has a similar structure as if you have a family of linear differential equations, the set of points where where the Galois group is smaller than the generic Galois group.
Okay, I missed these slides on the linearization and on the Galois group. So it's okay. It's a kind of Hilbert theorem that you are doing with the Galois group in searching where it's not this. So you, in fact, you are, in a certain sense, you are computing the groupoid, but up to order 1, the Lagrange groupoid, but only the first part of it.
Yeah, indeed. And what makes it work, that you only have to compute the first part of it, is because the equations are autonomous. And if you look at this case, which I think is even more interesting, I mentioned 3 cases here. So this one was solved recently. The proof I explained is the first case. The second case, I think the reason is that you need to look at higher at higher part of the group width to explain it, because there are reasons to explain why it's easier to prove that an autonomous differential equation is strongly minimal than a non-autonomous differential equation is strongly minimal. And
So,
this can be quantified. Yeah.
It's also related to my second question. So when you want strongly minimal, you need to add parameters. And when it's autonomous, the differential extension of C with the trivial derivation are easy to manage more than... no, it's not that. Is it possible to explain a little bit why it is you don't have these parameters?
So the first thing you still have many differential field extension of C0, but the first part of the proof is to find an equivalent formulation of strong minimality that doesn't involve going to differential field extension, or that involve only you have to control what kind of differential extension you have. And indeed, you can always assume it's essentially enough to look at a differential extension that will be a Picard-Vecchio extension or a strongly normal extension. And in the case of C, indeed, there's not that many extension of this form, and so this simplifies a lot the system. And so the best way to explain that I know is that there's James and Rahim introduce an integer that measures how hard it is to show that the system is strongly minimal. And so this is called the non-minimality degree. And in the case of autonomous case, this non-minimality degree is always less or equal to 1. And in the case of equations which are not autonomous, this non-minimality degree can take essentially 3, less or equal to 2, but it can take 3 different values, and it's harder to understand all the possible cases. This comes indeed from the fact that linear equations have very simple groups over the constant, and over C of t, they have arbitrary complicated Galois group. And also, to distinguish an equation which is strongly minimal from an equation that has Galois group, let's say PSL3, is very hard. I mean, it's hard. It's hard in the ODE case. In the autonomous case, you don't have to do that. And so you end up having to manipulate simpler geometric arguments. And I indeed think this is an interesting field to study this.
Thank you.
Any other questions? So I have 2 quickly. So I'll ask both. First, any progress on the fine structure? So you know that it's strongly minimal, and because it's autonomous, it's trivial. Can you tell whether it's omega categorical or not? And my second question.
So
yeah, you want to answer that? Yeah. Right.
Yeah. So I don't know how to do that. Mm-hmm. Right. I think this is a very interesting question. But again, I think that one way when I looked at your work on Pan-Levé equation, what plays a key role is to understand this exceptional locus. Right. And to understand, and because this exceptional locus here will be the risk-density in your set. And so one way to try to answer this question is to try to understand the film structure of this exceptional locus where it's not strongly minimal and you can compute. And then to try to say that if it was not omega categorical, so I don't know if it is omega categorical or not, but of course, I mean, I don't know how to prove it, but of course, the conjecture is that they are strictly disintegrated.
And to add to that, so I guess if you were to be given 2 different, let's say, mutually generic systems, you would want to prove that there are no such correspondences as you define, right? And
yes,
you would have to play the game.
Okay.
Yeah, you can do that.
Mutually. Yeah, this is okay. But because the family depends on so many parameters,
right?
You know, here I think here. So using this exceptional locus, you can. But here it's just that you have so many parameters in your family that actually you want to study a bit smaller families, subfamilies of one parameter that you pick inside this family. But if you allow all parameters, I know that if you take two independent algebra, I mean, if the coefficient of two systems are algebraically independent and both satisfy no Q algebraic relations, then the solutions have no Q algebraic relation. But I would like to get something a little bit more precise. For example, I don't know even if they are. I'd like to describe more precisely which systems are in algebraic correspondence, which is also something I don't know how to do at all. But in the generic, if you assume everything is generic, this is okay.
All right. So I think it's very late where Rémi is. Thanks. Let's thank him again for his great talk, and thanks everyone for being here.